Hi, my name is Grace, and today I will be presenting my final project, Phase 2, for discretes. Now, the problem that we would like to solve is we would like to prove using induction that 9 to the n minus 1 is divisible by 8 for all positive integers n greater than 0. Now, when I just got this problem, I didn't really know where to start because I had no clue that it was true in the first place. So what I did was I wrote a bunch of test cases out where n equaled simple numbers 1 through 5, and I plugged them in into 9 to the n minus 1. From here, I checked that if they were all divisible by 8, and sure enough, they were. So because I was able to write out a bunch of test cases and check if these were true or not, I was able to start formulating an idea, which helped me start my proof. Now, because we want to prove that this is true using induction, it'd be a good idea to introduce what induction is. Induction is a mathematical technique used to prove that a statement, theorem, or formula is true for every natural number. It involves two steps, a base case and an inductive step. The base case is where we prove usually that P of 1 or P of 0 is true, which is often usually just the first case. And then our inductive step is assuming that a arbitrary number k in the middle is true, then the next k plus 1 is also true. I included a picture of dominoes because I believed it was a pretty good example of this. The first one, if we can prove the first one is pushed down, then that is true. But then for the inductive step, if one of the dominoes in the middle falls, then it automatically pushes the next domino down, which is what we want to do with the inductive step. If one of them is true, we want to prove that the next one is also true, purely based on that information. Now here we'd like to start with proving the base case. Let P of n equal 9 to the n minus 1, and because it is our base case, let's start off with our first integer where n equals 1. From here, we would just like to plug 1 into our equation where we get 9 to the 1 minus 1. Overall, that simplifies down to 8, and we know 8 is divisible by 8 because it is a multiple of itself, and also because when you divide it, it gives us an integer. So because of that, we have been able to prove the base case. Now for inductive hypothesis, we would like to assume that P of n is true for all arbitrary values of k. Now consider the inductive hypothesis for an arbitrary k, where P of n is true for all values of k. Now, we would like to prove that if P of k is true, then P of k plus 1 is also true. So to start off our inductive step, we'd like to plug in P of k plus 1. That'll give us 9 to the k plus 1 minus 1, and then we can simplify that down to 9 to the k times 9 minus 1. Because earlier we had just assumed in our inductive hypothesis that 9 to the k minus 1, or our P of n, is divisible by 8 for all values of k greater than 0, we're able to replace 9 to the k with 8 to the n plus 1. We have 8n because we know that 9 to the k minus 1 is divisible by 8, so 8 times something would obviously equal the former. And then we also add the 1 for basic arithmetic sake, and so that way we can isolate our 9k. When we plug that in, that gives us 8 to the n plus 1 times 9 minus 1, and then using basic math skills, we can just deduce that down to 72n plus 9 minus 1, which equals 72n plus 8, which equals 8 to the 9n plus 1. We're able to factor out an 8 here, and that also, using our law of divisibility, proves that it is divisible by 8 for k plus 1 because 8 is being multiplied to our equation, which means that it can also be divided out and we'll still be left with whole numbers, thus proving our inductive step true because we were just able to show that no matter what k or m equals, it'll always be divisible by 8, which is what we want to prove. Thus, because we have been able to prove that the base case P of 1 is true and that we've proved that P of k implies P of k plus 1, P of n is thus divisible by 8 for all positive integers n greater than 0. Thank you.